All right. So we've talked about the structure of the atom, right? You guys know where the protons, neutrons, electrons are located. And let's talk about the nucleus for a second. I'm going to back up here so we have a little bit of room. In the nucleus, we know that the protons and neutrons are present. Now, if you recall, when we first started talking about the electron, we started talking about things that are charged. And when things have the same charge, what happens? They repel from each other, right? So in the nucleus, I've got a bunch of protons, which are all carrying a positive charge. The neutrons have no charge. So one of the reasons why the nucleus does not fly apart is because you actually have neutrons in between. It's kind of like when there's 3 kids in the family and 2 really don't get along. You stick the 1 kid in between them, right, to space them out, act as a buffer. That's what neutrons are kind of doing. They're preventing the protons from having direct contact. Okay? Because if you put 2 protons literally next to each other, they would push off of one another, and that would be bad. So, the thing is, this only works to a point, right? And then some changes have to be made. So if we were to look at the periodic table, if you look at, say, neon, right, element 10, and if you see the mass number for neon, do you see how it's rounded to 20? Okay, for those of you close enough to a periodic table, right? The neon's mass is rounded to 20, and its atomic number is 10. So if neon has 10 protons and a mass of 20, how many neutrons does it have? 10. Okay. Now, if we move further down on the periodic table, let's say we look at something like krypton. Right, so krypton's atomic number is 36, but the mass number for krypton is 84. Okay, so 84 minus 36 is your number of neutrons. So that's, 48? 48 neutrons. Where's this head? 10 neutrons. Okay, so let's move further down. Let's look at xenon. Xenon has 54 protons. Xenon's mass is 131. Okay. So 131, we're looking at 70. How many neutrons do we have there? 130 minus 50 would be 80. 76. So 77. 77 neutrons. Based on these 3 examples, what can you tell me about elements as their atomic number increases? What can you tell me about them?
More neutrons than protons.
Yes. The larger the atomic number, the more neutrons are seen, are observed. Okay? And so this is because when you have a small number of protons, it's easy to just stick neutrons in between to make sure the protons don't touch. But you start increasing the number of protons, all of a sudden there's more and more angles to which protons can be near each other. This is geometric growth. It's not linear. So the more protons you have, all of a sudden you're going to need 3 neutrons, whereas before you would be able to get away with 2. So we need more neutrons as the atomic number increases. So this chart right here, this is probably one of the important graphs. This is the most important graph of this unit. This is called the band of stability. So we start out by graphing the neutrons on the Y and the protons, or atomic number, on the X. All right, so notice that we have a line, a pink line here, where the slope is 1. Right, that line represents a slope of 1. What this chart shows you is what the necessary number of neutrons is in order to be stable. Each one of these dots represents a stable ratio between neutrons to protons. So going back to the first couple of examples that we did, we talked about neon, right? So neon was atomic number 10. Atomic number 10 has about 1 neutron for every 1 proton. That is a slope of 1, and that should make sense because it aligns with the red line. Anyone see that? If I were to say, what's the slope for that section right there? The slope here is 1 neutron for every 1 proton. But notice how that band starts to peel upward, and its slope now starts to become greater than 1. So now we have an area here where the slope would be 1.1 neutrons for every 1 proton. And then it goes up even still, 1.2 neutrons per 1 proton. 1.3 to 1. 1.4 to 1. And the very top, 1.5 neutrons to 1 proton. These ratios dictate when a nucleus is going to be stable. So, what happens if the ratio is wrong? What if we have an element here represented by this blue dot right here? That ratio has too many neutrons per proton. And that's actually going to be destabilizing. So if it is off of the main band, it is unstable. What if it is below the band? Oops. Like here. This, if it's below the band, it has too few neutrons. Also unstable. So in other words, the only way to be stable is to have the correct ratio, to be on that band, that dotted line. That is the only way that your isotope is going to be stable. So, whether an isotope is going to be stable or not literally depends on if its ratio falls somewhere on that band. Okay, so let me give you some examples then. What if we have an element with 15 protons and 15 neutrons? Actually, that's not an example. I'm going to exaggerate this just to prove a point. Let's change that. 15 protons, 10 neutrons. Where does that fall on the band? Does it fall above the band or below the band? Below. Stable or unstable? Unstable. It's unstable, right? All right, let's do another one. What if we have 100 protons and 149 neutrons? So when you have 100 protons that actually isn't even on this chart, right? So let's extrapolate. You guys know what that word extrapolate means, right? Just to make guesses outside the boundary of known value, right? So 100 would be here. If this chart were to go on, right? We would need a mass of roughly, I don't know, 180, 190. I'm sorry, number of neutrons. We would need roughly about 180 neutrons, and we're not even close to that, right? So 149 neutrons puts us about here, which is below the band, which is unstable. Okay. Does this make sense how to read this chart? You've got to know this inside and out. I might even ask you to draw this and label the important parts. Okay, so this is an important thing. This is going to be our guideline as to figuring out whether something is stable or not. Okay, so we talked about it, the number of neutrons being important for stability. We should talk about another term too, and that's called the strong nuclear force. So in the nucleus, yes, you have the protons being separated by neutrons, but there's also another force which is outside the scope of this class, and therefore we're not going to study it, but it's more so like a nuclear physics concept called the strong nuclear force, which overcomes the repulsions between protons, and it's basically acting as a glue. Right, it's a glue that keeps neutrons bound to protons. And that also helps stabilize the nucleus. So much like how we talked about when they discovered the electron, everybody was so shocked that there's something that is smaller than the atom, right? Well, it turns out that even electrons are made up of other things. And the characteristics of the things that they're made up of result in this strong nuclear force. And it's way outside what we can talk about competently. But we're just going to call it that. So, in essence, when asked, what are the reasons why a nucleus is stable, you can cite the strong nuclear force, and you can cite the correct ratio of neutrons to protons. Okay? All right. So that's all well and good. We know how to predict if something is stable or not in the nucleus. What happens when it is unstable? Well, when it's unstable, then we get, I keep tapping the wrong thing. We get what's called nuclear decay. Nuclear decay is the breakdown of the nucleus. And this can be really bad. Not always, but it can be really bad. This is whenever you think bad things happening about nuclear physics and, bombs and power plants and stuff like that, it's because there's some instability going on. So, imagine a nucleus that's unstable. And when it's unstable, it's just not long for this world. Something's got to give. And so what's going to happen is particles will be shot out. A radioactive particle. And we talked about these radioactive particles when we talked about Rutherford, how Rutherford used alpha particles, and how he also studied beta particles and gamma. So to classify the particles that could be shot out of the nucleus, essentially there's these types right here. The alpha we already talked about. The alpha is also known as the nucleus of helium. The symbol is that funny Greek letter A right there. Because the alpha particle has 2 protons, it's got a charge of +2. And as far as penetration, it's pretty low. Alpha particles, they can go through things that are really, really thin, but they can't travel very far. Right? So if there was a source of alpha radiation sitting where I am right now, you guys in the front row, it probably wouldn't even reach you. It'd be like shot out at you, but then it would just kind of like fall and peter off by your feet. Okay, so alpha radiation itself is not dangerous. Okay. Then there's beta. So beta is known as essentially an electron. It has the same characteristics as electron. It's not exactly the same because a regular electron and a beta particle don't come from the same place. A beta is an electron that comes from the nucleus. But it's like the same mass, it is the same energy. Symbol we use is a B, right? Capital B. To fill in some numbers here, I guess we can go ahead and write this on it. It's got a -1 atomic number, but it's got a mass of 0. So that's the symbol we use. I should go back and fix the alpha as well. The alpha has atomic number 2 and a mass of 4. Okay, so the beta has a charge of -1. And as far as penetration ability, it's medium. You know, if you're wearing like a hoodie and a t-shirt underneath it, that would be enough. That would be sufficient to stop a beta particle. Right? It has more penetration ability than an alpha, but not much more. Okay? And then there is gamma. And gamma, this is the bad one. This is the one that's like, look out. We're worried about gamma radiation because that's the one that does damage to living things. It's very high energy. It's actually considered a non-particle. The symbol for gamma is, remember we called it an upside down cursive L? It's not considered to have mass and it doesn't have an atomic count. So 0, 0. It's got high penetration power. We can stop it with lead, which is why Rutherford, when he was setting up his gold foil experiment, the uranium was actually emitting alpha and gamma, and so he had to protect himself from the gamma, which is why he had the lead block, and he was standing behind it. Okay, so whenever there's any kind of nuclear issue wherever, one of the first things they do is they take in a detector. It's called a Geiger counter. And then they'll walk around and it's this little wand that they wave around and it makes little clicking sounds. And if the clicking sounds increases, then there's a radiation source. Right? It's verified that there's some kind of leak and then they'll do what they need to do to fix it. If you've been in a government building that was built in the late 60s or early 70s, probably there's a fallout shelter in the basement. You see, when there were tensions between the US and Russia, it was called the arms race. And so we would build more nuclear warheads. And then that would prompt them to build more nuclear warheads. And so all of a sudden, the countries were doing this in terms of how many nuclear warheads they had built. And so there was a genuine fear that if something caused the other country to just snap and like launch their nukes, then we needed places for the citizens to go hide and be safe and be protected from the radiation that would come from the missiles. So there's fallout shelters. So a fallout shelter is structure underneath a large building, and the walls have to be several feet thick of concrete, right? So you see how we say how the radiation is stopped by lead? Yeah, it can be stopped by 6 inches of lead, but to make that part of a building, that's too much lead. That's too expensive, right? So it's cheaper to build a shelter made out of concrete, right? And so like 3 to 4 feet of concrete would be sufficient, I think, to stop the gamma radiation from coming in from the outside. Maybe you've seen a symbol like this before. This is the symbol for radiation danger. You've seen, I don't know if you've seen that. Ever seen Back to the Future? Marty's yellow jacket has that on the back, right? Okay. All right, so gamma radiation is what we are afraid of. And we'll talk about the things it does to, in a different class. And then the fourth type is just a neutron. A neutron can be emitted from the nucleus. Neutron symbol is N. It has a mass of 1, but doesn't have an atomic count, so the atomic number is 0. And it also has low penetrating ability. So if you base this on the mass, if you look at the masses of our particles here, the heaviest one has the lowest ability, and the lightest one has the strongest ability. Right? So your penetration power is inversely related to the mass. So because neutron is the second heaviest, it's also, just barely more dangerous than an alpha, just barely. Okay? All right. So when these going back to this crude picture I drew over here, when you have an unstable nucleus, particles get emitted. Now, depending on what that particle is, the nucleus is going to change. So if it was an alpha particle, then it would be made up of 2 protons and 2 neutrons. So if it were protons and neutrons that were leaving, then our nucleus would have a gap, because those protons and neutrons had to come from somewhere. They literally came from the nucleus. Now, the problem with that is that the forces, that strong nuclear force we talked about here, by having part of the nucleus shoot out, the forces are not distributed equally anymore. You ever dig with a shovel at the beach? Like dig a hole in the sand, but no matter what, at some point you can't stop the sand from filling in right after you dig it? Okay, so the similar thing is going to happen here with the nucleus. These protons and neutrons, with this asymmetry that now exists here because that thing was shot out of there, they need to rearrange themselves to balance their attractions and repulsions. And so that process is going to emit, as new attractions and new positions are formed when these guys rearrange, this is going to emit a lot of energy. And that energy comes in the form of gamma. Imagine taking a ball of Play-Doh and then taking, let's say your dog takes a bite out of it. Could you take that ball of dough that has a bite out of it, but reshape it into another ball again and hide the fact that there was a gap? Sure you could, right? And that's kind of what's happening to the nucleus. But in the process of doing that, energy has to be expended, has to be released. Okay? All right. So, as far as recognizing what is happening during nuclear decay, we write what are called nuclear equations. And a nuclear equation, the main rule about a nuclear equation, and really about any kind of chemical equation, is the law of conservation of matter. Right? Your total mass before and your total mass after are going to be the same. So, what we start with on the left, this is our radioactive isotope, is what you begin with. And I know the number's a little wonky, so I'm going to rewrite this so it's cleaner. So the mass number is 238 on this isotope, and the atomic number is 92. This particular ratio, if I subtracted out the atomic number and got the number of neutrons, it would be seen that this is unstable. Hence, it is radioactive. Okay. When something's radioactive, it's going to emit one of those types of radiation that we just mentioned. This first example, it's emitting an alpha particle. When something emits an alpha particle, the total mass on the left must equal the total mass on the right. Just by looking at what we have here so far, what is the total mass on the left? I.e., what's the mass number? 238. Okay, so what that means is then on the right side, the sum of the mass numbers must be 238. If an alpha particle has a mass of 4, that means this other thing has a mass of 234. Same rule applies for atomic number. If the atomic number is 92 on the left, then the sum of atomic numbers on the right must also be 92, which means this is going to be atomic number 90, which means this is going to be thorium. It's just balance. Your atomic numbers and your masses have to balance. The left side and right side must be balanced. Now, this process, notice that we created a new element. This something started as uranium and now became thorium. When this happens, this is what we call transmutation. The changing of an element into a new element through nuclear decay. Yeah, question?
Wait, can you actually like change like lead into gold or something like that?
Okay, so you cannot, but a radioactive atom itself can, but you can't control something that is nuclear, that's radioactive. If something is radioactive, it is because it has an imbalance of neutrons, protons, but you cannot influence that in any way. If something is radioactive, you cannot stop it from being radioactive, and if something is not radioactive, you cannot make it radioactive. It's just got to be the way it naturally is. Okay, so no. All right. So these equations that we write need to just follow that simple rule. The numbers on the left and the numbers on the right must match up. Let's try the next one. Alpha decay of Pa-231. So the isotope is Pa, which is protactinium. So I start by writing Pa. The mass is 231. The atomic number for Pa is 91. And they're saying this is alpha decay. So here's an alpha particle being emitted. And so the question is, what is the new element? Well, just use arithmetic. Your total mass on the left has to be 231, which means the total mass of this new particle is going to be what? Yeah.
89?
Sorry, top number first.
Okay, 227.
227 is the mass of this new element. And yes, the atomic number goes down by 2, meaning it's now 89. 89 is actinium. Okay, so let's try a second example, but this time it's a beta particle being released. So we start with francium. The mass is 223. The atomic number of francium is 87. I wrote it on the right side this time. It doesn't matter if the numbers are on the left or the right. It's a beta particle, so betas have no mass, but they have an atomic number of -1. So because the mass is unaffected, the mass is going to stay 223. The question is, what atomic number makes sense in order for this equation to be valid? 88, yes, because 88 and a -1 give you 87. 88 is radium. Do these examples make sense, guys? Your numbers have to match on the left and right side, okay? Now, other observation to make. Notice how when an alpha particle is emitted, the new element's atomic number goes down. But when a beta particle is released, the new element's atomic number went up. Okay, so that's kind of important to notice, okay? Alpha particles decrease atomic number, beta particles increase atomic number. So beta emissions increase atomic number. Okay. All right. That's as far as I wanted to get to today. So we're done here.